Hey class, how you doing? I wanted to record another video of 2D momentum and actually incorporate some work and energy concepts into a 2D momentum problem. So to help prepare you for the integrated assessment. You likely won't see a 2D momentum with the work and energy. It'll probably be 1D, but let's practice both because we need to practice both anyways. So we're going to go curling. So curling's a nice sport where you throw stones along the ice and you land in the middle, and it's kind of like shuffleboard. You try and land your stones in the middle and knock the other player's stones out when you can. So what we're doing is we're going to be blue, and we're trying to knock the red stones out. And so when we're 10 meters out, we release the stone at a velocity of 3.3 meters per second. And it slides along the ice, and the ice actually has a coefficient of friction of 0.04, so pretty slow. But we know our stone is going to be slowing down as it kind of gets closer. And then it hits the red stones. There's two red stones near the bullseye, and the blue stone stops after it hits, and the red stones continue on. One gets knocked 70 degrees away from the vertical direction, and one gets knocked 70 degrees down away from this horizontal line. All the stones have a mass of 0.8 kilograms, and we want to know how far do the red stones go before they stop, before friction brings them to a stop. And we want to know, do they get knocked out of this circle? Because if you stay inside this circle, the red team can get points. So we want to knock them out. So yeah, this is the ultimate question that we need to answer. How far do the red stones go before they stop? And you might look at this question and think, whoa, what the heck is going on? How can I solve this? Anytime you see a complicated problem, one strategy is to break it into pieces that you understand and kind of start thinking about those individual pieces. And then you want to think about how those pieces connect together. All right, so I'll take you through my thinking. So we released it at an initial velocity of 3.3 meters per second, but we know that the stone is going to be slowing down while it travels these 10 meters, and it's going to be going at a slower velocity by the time it hits the red stones. So what's going to be the acceleration of the stone while it's sliding on the ice? We're going to need to know that, I'm pretty sure. Well, for that we can draw a free body diagram, right? And so if we're looking like at a cross section, it's sliding on the ice. We have the weight going down into the ice, the normal force of the ice pushing back up on the stone, and then the coefficient of the kinetic friction force pushing the other way. And so if we wanted to write Newton's second law, the sum of the forces in the x direction, the only force acting in the x direction is friction, which is acting in the negative x direction. We know the kinetic friction force is equal to the normal force plus the coefficient of friction, which we said is 0.04. And as you can see, the acceleration in and out of the ice is going to be 0, so the normal force is going to be equal to the weight, mg. So negative mg times the coefficient of friction is going to be equal to the mass times the acceleration in the x direction. Mass cancels out. So the acceleration in the x direction is going to be equal to negative g times the coefficient of friction. So now we can solve the first part that we think we need to know. How fast is the blue stone going when it hits the other two red stones? So we can use this kinematic equation. We could use work energy concepts as well, but this works just as well. So we know that after traveling a certain distance, delta x, while it's accelerating, the final velocity squared is going to equal the initial velocity squared plus 2 times the acceleration times the distance it travels. So we can just take the square root of this expression to get the final velocity of the blue stone before it hits. And we plug in The distance traveled is 10. The acceleration is negative g times mu k. That 2 is still there. And we plug in 3.3 for the initial velocity. We find that the stone hits at a velocity of 1.746 meters per second. All right, so the next thing that happens in the problem is a transfer of momentum, right, from the blue stone to the red stones. So we can think about what are the initial velocity of the red stones after the collision, because the red stones are going to initially be moving, or they're sitting still before the blue stone hits it, and then they're going to be moving at some initial velocity after the collision, and then they're going to be moving, and then they're going to slowly come to a stop after friction slows them down. But we want to know right after the collision, how fast are the red stones moving. So we want to think about moments, just mere moments after the collision. We know that the momentum in the x direction for the whole system is going to equal the momentum in the x direction after the collision. So the momentum before the collision is entirely in the blue stone since the red stones are still, and we're moving completely in the x direction, so we just have 0.8 kilograms times 1.46 meters per second. That's how fast the blue stone's going just before it hits. That's our momentum before the collision. So that's going to equal the momentum in the x direction after the collision, right? And the momentum in the x direction after the collision is going to comprise of the movement of the two red stones, since the blue stone has a velocity of 0 after the collision, we said. All right, so to think about that, remember, we're going to have the mass of the first red stone times its x velocity, plus the mass of the second red stone plus its x velocity. All right, and we can break up the velocity into components, right? If the top one is called V3, the stone number 3, this is stone number 3, this is stone number 2, let's say. This is V3. We want to think about the x component of its velocity. So we look at this right triangle, right? And the x direction is opposite of this 70-degree angle. So the x V3x is equal to the magnitude V3 times sine of 70 degrees. All right, what about for this one? For this one, we give the angle from a slightly different location, right? We give the angle from the horizontal. And here you can see that the x component is actually adjacent to this 70 degrees for V2. So V2x is equal to V2 times cosine of 70 degrees. All right, so let's say that wraps up our x components. We don't know what to do with that because we have two unknowns, and that's scary. So we need to use another equation in order to figure things out. So let's think about the momentum in the y direction. The momentum in the y direction before the collision is 0, right? Because the blue stone is just moving perfectly horizontally. It's not moving in the y direction at all. So the momentum in the y direction is 0. That equals the momentum in the y direction after the collision, which is going to include the y component of this guy's velocity and the y component of this guy's velocity. So mass times the y velocity for the third stone minus the mass times the y velocity for the second stone. You can see mass can cancel out. So the y velocity of the second stone has to equal the y velocity of the third stone. And again, we can express those in terms of the velocity magnitude. We find that V2 sine of 70 degrees equals V3 times cosine of 70 degrees. And then what do? We have two equations and two unknowns. We express one unknown in terms of the other, and we make a substitution into the first equation. right? And when we do that, and when we solve the fun trigonometry, we find that the velocity of the third stone, this one, after the collision is 1.4 meters per second. All right, and then we can simply plug that answer back into here, and we find that the velocity of the second stone after the collision is going a little slower. It's going at 0.487 meters per second. All right, good. So we've solved this piece of the puzzle. What are the initial velocities of the redstone just after the collision? But then what we really want to know is how far does each redstone go before it stops? So we can go back to thinking about our kinematic equation that we kind of did in the beginning for the blue stone. Think about after it stops, the final velocity of the stone is going to be 0, right? And we can plug in the velocity just after the collision as our initial velocity. And what's the acceleration going to be? Well, it's still sliding on the ice with the same coefficient of friction. So the acceleration is going to be the same as the blue stones was. It's going to be negative gravity times the coefficient of friction, negative 0.392. So we can plug that in. So for stone number 2, that's moving a little bit slower, we plug that in as our initial velocity after the collision. And we solve for how far does it go before it reaches a velocity of 0. And we find that it travels 0.303 meters before it stops. For stone 3, which was going a little bit faster after the collision of 1.4 meters per second, we solve for how far it goes, and we find that it goes 2.5 meters before coming to a stop. So there you have it. There's our answer. One stone got knocked out of the circle. This guy got knocked out, landed over here. But this guy only got knocked about 0.3 meters. He just went a little ways because he didn't get enough of this guy's momentum to really get knocked that far. All right, so hopefully that was a useful video, and you can use this in your studies. All right, see you tomorrow.